Hello Year 12. We are picking up again now on Chapter 5, Radians, Exercise 5e. I will recap converting between degrees and radians, as well as using trig graphs or the cast diagram from Year 1 work to find all solutions in a given range to trig equations. If you're really confident with that work, then please feel free to skip straight to these examples and then crack on with the exercise. So we can measure angles in radians or degrees. The key conversion to remember is 180 degrees is pi radians, and we can use this fact to work out mentally some basic conversions. For example, 90 degrees would be pi over 2 radians, 60 degrees would be pi over 3 radians, and pi over 6 would be 180 divided by 6 would be 30 degrees. Pause the video and answer the questions on the right. These are the answers that you should have got. 45 degrees is pi over 4 radians, 360 degrees 2 pi radians, 18 degrees and 120 degrees. Where we don't have some nice easy numbers to work with, for example 100 degrees or 2.4 radians, we can just use our standard approach to converting units. To move from degrees to radians, I divide by 180 and I times by pi. So for example, 100 degrees, I like to use the conversion method, the unit conversion method. So I've got pi radians divided by 180 degrees. You can see here that this is equal to 1 because pi radians 180 degrees are the same. We're converting from degrees to radians, so we're dividing by 180 to get rid of the degrees, and then we're multiplying by pi to bring in the radians. So that's how I remember that. That just then gives us 5/9 of pi, and I might wish to evaluate that, round it to 1.75 radians. Working back the other way from pi to 180, we're getting rid of the radians, so we're going to be dividing by pi, and then we're getting to degrees, so we're going to times by 180. So divide by pi times by 180. Here 2.4 radians, dividing by the pi to get rid of the radian measure and introducing the 180 degrees. That takes us to 137.5 degrees. Okay, pause the video and answer the questions below. And then mark your work. Moving on here to sketching graphs of trig functions. Nothing has changed here at all. The sine graph and cosine graph are the same. The only difference is that we can replace the scale on the x-axis. Instead of degrees, we can replace it with radians. So you can see pi radians in place of 180 degrees, 2 pi radians in place of 360. We can also use the cast diagram with radians instead of degrees. So instead of my angle from 0 halfway around the circle being 180 degrees, I go from 0 to pi, 3 pi over 2 and back to 2 pi. So I'm going to remind you how to find all solutions in a given range when solving trig equations. Reminder that your calculator only returns the single principal solution, and then we can use these facts to work out all other solutions in the range. So if your principal solution was found from doing inverse sine, then you can subtract that from 180 to find another solution. If your principal solution was from inverse cos, then subtract it from 360 to find a second solution. Once you've got these two solutions for sine or cos, they repeat every 360 degrees, so you can just add or subtract 360 to each of those solutions and find as many other solutions as you need. If it's inverse tan, then tan repeats every 180, so you add or subtract 180 as many times as needed in the range given. So that's if we're working in degrees. It's exactly the same if we're working in radians. If you're solving a trig equation given in radians, then when you've found your principal solution from inverse sine, subtract your answer from pi. If you found your principal solution from inverse cos, subtract your answer from 2 pi. They then repeat every 2 pi, so for sine and cos, when you've got your two solutions, add or subtract 2 pi to each of them to find multiple solutions. For tan, it's just pi. Find your principal solution, add or subtract pi as many times as you need. So before I go any further, I just wanted to stress the equivalence here of degrees and radians and ensuring your calculator is in the correct mode. First of all, change your calculator into radians and evaluate cos of 4 pi over 3. You should get -1/2. Then change your calculator into degrees, evaluate cos 240, you'll get the same thing. Just make sure your calculator is in the correct mode as to what you need it to be. Okay, if you're asked to evaluate something like cos of 4 pi over 3, you can convert it to degrees first and then do as you would normally do, as you would have done in the past, find equivalent values. Cos 240 is the same as cos 120. That's the same as minus cos 60, which is -1/2. And we've reduced it down to a trig value, an exact value that we know. Now, to recap, if you're not confident on that, where that comes from is the symmetries in the cosine graph here. So a reminder of how these equivalences work. We're symmetrical around 360 here for the cos graph, and I'm looking at cos 240. It's 60 degrees above 180. It's going to be the same value as 60 degrees below 180. So we can see cos 120 and cos 240 must be identical. If I then look at 120 is 30 degrees above 90, it's going to be the same as 30 degrees below 90, but the opposite sign. So so cos of 120 is the same as cos 60, but it's negative. Okay, that's where that comes from. I think it's easier to use the cast diagram. If we're looking at cos 240, we start at 0. You travel around 240 degrees. That takes us 60 degrees past 180. And if I'm looking at cos 240, that will be the same as cos of the angle made with the acute angle made with the x-axis here. So cos 240 is the same as cos 60. You can write that down. But then we look at the sign, okay? And the sign here is cos is always positive here. They're all positive here. Sine is positive here and tan is positive here. So here tan is positive, cos must be negative. So I can go straight here from cos 240 is the same as cos 60 and it's minus. And then I know cos 60 is 1/2, so it's -1/2. So I don't think you need to convert it into degrees. If you're asked for cos of 4 pi over 3, actually you can go straight to the cast diagram, and I think this is probably the easiest way. So 4 pi over 3, we go from 0 to pi and we go another third of pi around. And here we can see that cos of 4 pi over 3 must be the same as cos of pi over 3, the acute angle made with the x-axis, and it's negative in that quadrant. Cos of pi over 3, this is where we recognise it as cos 60 or 1/2. I'm going to go straight to the answer there. Equally, you could use the cos graph with your angles in radians there, and it's the same principles as before. So another example here, this time we're looking at sine of -7 pi over 6. So you've got several different things you could do. You can convert to degrees, you can use your trig graph, or you can use the cast diagram. I'd encourage the cast diagram. Personally, think it's easier. If we have a look at here, this time -7 pi over 6. So start at 0, go round to -pi. That would be 6 pi over 6, and I need to go another pi over 6. So I'll be up here in this quadrant. So mark that on. I've gone 7 pi over 6, so minus 7 pi over 6. Sine of that must be the same as sine of the acute angle made with the x-axis. So I can see here directly sine of minus 7 pi over 6 is the same as that. And this in this quadrant, CAST, sine is positive, so it's just that. And sine of pi over 6, same as sine of 30, is 1/2. So here we have the question, or to solve the equation, sine 3 theta is √3 over 2, and we're given this interval. First thing we'll notice that the argument here is sine 3 theta, not sine theta. So we need to amend our range there. So instead of for theta between 0 and 2 pi, we need to be looking at 3 theta between 0 and 6 pi. Once we've done that, you can do inverse sine of √3 over 2. Well, we know that that's pi over 3. So that's our principal solution. That's our first one. 3 theta must be pi over 3. We can also know in this range here from 0 to 6 pi, we've basically got 3 cycles of the sine graph. So 1, 2, 3. My first solution that I found was inverse sine of √3 over 2 is 60 degrees, pi over 3 is going to be there. Well, I can see that I must have another one that's pi minus that. And then if I add 2 pi to each of those, I'm going to get those solutions. Add 2 pi again, I'm going to get those solutions. So I can see that there are 2 solutions in one cycle. There must be 6 solutions that we're looking for. So once I have found pi over 3, I can take that away from pi to get 2 pi over 3 is my second solution in the interval. My next solution pair, which is here, is just adding 2 pi to each of those. So if I add 2 pi to pi over 3, so that's 6 pi over 3 plus pi over 3. So if I add 6 pi to each of those, I'll get 6 pi over 3 to each of those, I'll get 7 pi over 3 and 8 pi over 3, and then add another 6 pi over 3 to each of those. That gives me my 6 solutions in the range. That's 3 theta, and I need to find all of my solutions for 3 theta before I then start amending that and dividing everything through by 3, and I get my final 6 solutions. I could equally do this with the cast diagram. So here, when I found that my first solution was pi over 3, I know that sine is positive in this quadrant, sine is also positive in this quadrant. So sine of pi over 3 must be equal to sine of 2 pi over 3. If I travel all the way around there, I can see that that must be 7 pi over 3 to get me back there. And then 8 pi over 3 gets me here, travel around back here again, and this will take me to 13 pi over 3 and then 14 pi over 3. I can do that by going around that cast circle. Okay, next example here, we're asked to solve this trig equation. We know we're in radians because the interval is given as x between 0 and 2 pi, and we're asked to give each solution in terms of pi, so we want exact values here. So first step in this is to try and get the equation in terms of a single trig function. We can use our identity that sine squared plus cos squared equals 1 to replace this cos squared part of it. So cos squared is equal to 1 minus sine squared. Plug that in, multiply it out, rearrange it into our sort of hidden quadratic in sine x, and solve that quadratic. Here it factorizes, so we get 2 sine squared x plus 6 sine x minus 3 equals 0, and then solve for each of those brackets. So for our first bracket, we get sine x equals 1/2. Our second bracket, we get sine x is -3. That's not possible. Sine x has got a range of -1 to +1, so we can reject that second bracket. We're only therefore looking at sine x equals 1/2. That's what we need to solve. Our principal solution there is x is pi/6. We got that from inverse sine, or from knowledge of our exact values. So first solution from inverse sine is pi/6. Subtract that from pi and we will get 5π/6. So we've got our two solutions, pi/6 and 5π/6, and there are only two solutions in that given range. Okay, over to you for exercise 5e. Please do contact us and ask for any help on any of the questions that do come up. Thank you.